I have the good fortune today to be talking about the piece of work we did a little while ago with a very good friend of mine, Mr. Trevor Harris, who's one of my colleagues at the National Research Council. The work I'll be talking about was part of a larger study, and we didn't originally plan to do the work that I'm presenting, but it fell out of the study sort of naturally. We were tasked by the Canadian Coast Guard to do an evaluation of a new set of diesel spark-ignited diesel outboard engines for use aboard their fast rescue or fast inshore rescue craft. They wanted to know if they could move to a diesel outboard engine simply because it solves a lot of their operational and safety challenges associated with gasoline engines. Diesel's a lot more available and it's less flammable, so it solves a lot of their problems. So we embarked on a fairly comprehensive set of maneuvering, endurance, and seakeeping trials using one of their fast rescue craft outfitted with the new candidate engines. We spent a fair bit of time talking to the operators of the search and rescue craft throughout the study. We really wanted to make sure that whatever results we were going to provide were meaningful and would be useful in assessing the utility and the operation of the engines in that application. As we were talking to them, one of the things that came out that became really apparent was that a career spent operating fast rescue craft in a search and rescue role takes quite a toll, both physically and psychologically on the operators, the people that are involved in the work. Like I said, we hadn't set out to assess the psychological or the physiological load on the operators, but we put our minds together after the data was collected and had to think about how we could use some of the data that we had to do some of the assessment and understand a little bit more the interplay between the machinery and the human, so to speak. So we gave ourselves a couple goals, and we really wanted to assess over the course of the typical mission that we might expect to see. Two things, really. We wanted to understand how hard the operator must work to control the boat, and in a related sense, how successful they are in controlling the boat. And then we wanted to understand what the potential duration of a mission would be. So we included an assessment of fuel capacity, fuel economy, which allowed us to assess the maximum mission range based on the fuel capacity of the boat. So in order to use the data that we had collected, we turned to the automotive engineering world. And there's quite a body of literature in automotive engineering that's used to assess driver performance and driver effort. And most of that work is related to studies involving things like the effect of fatigue, the effect of impairment, the effect of distraction on driver performance. And the sets of data they use are basically broken down into two categories. They assess driver inputs. In the automotive world, those are primarily steering and throttle. And then they assess the outcomes of the driver inputs, which in the vehicle world are vehicle speed and lateral lane position. That data is looked at in a multitude of different ways in the automotive literature. We decided to pick two of the ways that it's looked at, which is looking at the standard deviation of the input signals as well as the frequency of the change in the input signals. And they also look at the standard deviation of vehicle speed. And all of that's quite analogous to the marine industry. Steering input and speed, of course, are directly comparable metrics between a boat and a car. The course or the direction the boat is being steered is analogous to lane position. And since we didn't directly measure throttle input, we decided to use engine speed as a proxy. So we used the engine speed from the two outboard engines to gauge the throttle input that was being done by the operator. The equipment that we used involved a data acquisition system that was outfitted aboard the boat. It was based around the onboard telemetry system of the engines. These were still relatively new production engines just out of the prototype stage. So the engine manufacturer was still quite active in measuring engine parameters and had an extensive telemetry system aboard. And that allowed us to get engine speed and fuel consumption quite easily. We supplemented that with a differential GPS to get vessel speed and course, and outfitted the vessel with a linear potentiometer to measure the angle between the outboard engines and the transom. And that gave us our steering input data. The vessel itself was a Zodiac Hurricane 753 outboard within the search and rescue configuration, which involves a driver plus two crew and we kept that same crew complement consistent throughout the tests. The engines were Mercury Marine DSI 3.0 spark ignited diesels. That in itself is relatively novel, but they were giving a combined power of 260 kilowatts, which is slightly lower than the gasoline variants that are used on the boat typically. Nonetheless, I'll point you to the table of principal particulars at the bottom of the screen there, and I will point out that 260 kilowatts in a boat that weighs 2,800 kilograms is pretty considerable power. The other thing I'll point out on the bottom right side there is the fuel capacity. And you'll note that the fuel weight is a significant portion of the total displacement of the vessel. So we made sure we topped up the fuel tanks before leaving the dock each morning to keep things consistent. I'm going to quickly show the general arrangement of the boat we used. You see forward, about midships on centerline, is the forward driver position, the steering wheel and throttle inputs. And aft to port and starboard are the two nearly identical navigator positions. I sat in the port seat throughout the tests with a search and rescue operator in the starboard navigator seat and of course in the driving seat. The other important equipment that we used through the test was a pair of wave buoys. We did our testing, at least the testing I'm going to talk about today was done over 3 days. On the first 2 days, we used a tri-axis directional wave buoy that was moored near the test sites. And the third day, we used a tri-axis mini wave buoy that was allowed to drift with a drogue down through the test area throughout the test. The tests were all conducted in eastern Newfoundland, which is on the east coast of Canada. The first test location highlighted with the red circle with the 1 is at the foot of a bay called Conception Bay. The wind and waves on that day were both from the southwest. So there's a relatively short fetch of wind-driven waves. They're quite short, steep waves. The second day of testing, this red circle with the 2 is basically the complete opposite conditions. Waves were approximately from the north-northeast. There's a couple things about this bay that make that, make that significant. First of all, the bay is very deep, particularly the mouth of the bay is between 200 and 300 meters in depth. And the fetch for those waves, if you continue directly out that bay, there's an area of open ocean, approximately 700 or 800 nautical miles, with the nearest land being the southern tip of Greenland. So despite being in a relatively sheltered inshore location, we were experiencing waves that are quite typical of offshore conditions. For the third day, we wanted to get a little bit more extreme set of waves to assess performance. So we moved off the mouth of St. John's Harbor. Those familiar with this area will know that that stretch of water is completely exposed to the North Atlantic. And with waves and wind coming in from the northeast, there's virtually no shelter in the test area. So we did get some pretty significant waves, which was exactly what we were looking for. The tests that we used in our assessment of the operator effort and success were a set of star patterns. The star patterns were devised to give us data at as many encounter angles with waves as we possibly could. We broke it down into 10 legs, which were all steered for a specific duration. That was just based on keeping the area of operation for the test at a reasonable level. For each of the legs, the driver was given a course and a speed and asked to maintain that for the duration of the leg, and they did their best job varying throttle and steering as they needed to maintain their course and speed. All of the data that we look at is based on a single leg of the star pattern, and we broke it down leg by leg and looked at the data individually. Our original plan was to test at a range of speeds between 4 and 38 knots, 38 being the maximum speed in flat water for this boat. You'll notice, however, that in the first wave state and the third wave state, we were unable to complete the test at 30 and 38 knots. And that just came down to safety concerns on behalf of the operators. They feared that, particularly in a non-emergency scenario, they were pushing the boat too hard if we exceeded the 20-knot threshold. You'll also notice in wave state 3, we were unable to complete the tests at 8 knots. And that was simply because the storm we were sort of in the beginning of was worsening throughout the test day. And despite the fact that we had a second fast rescue craft on standby throughout the testing, we decided that it was unsafe to continue testing through any more of that third day. So we cut things short. We looked at the data, both in time domain and frequency domain. And there's a couple things I'd like to point out at this point. On the bottom left, we're looking at a time domain or time history of the steering input. And what I've highlighted here with the red arrows is something that's quite characteristic of the inputs we saw, which is we see this adjust, hold. So the adjust, hold, adjust behavior. The driver would make a steering input and then wait for the vessel to begin to respond to that and then make it another steering input. So it's quite different from, say, an autopilot control or something like that. On the right-hand side, we have a frequency domain plot of the 4 channels that we're interested in. So heading, speed, steering, and engine RPM. And looking at the frequency domain was quite illuminating. We see that the heading and steering angle signals peak at a frequency of about 0.1, 0.12 hertz, and the speed and engine RPM peak at about 0.4, 0.45 hertz. This, of course, is for one single leg of one of the stars. So these data traces were slightly different for each of the legs we looked at. I'm showing some results here. I don't plan to dive into them very much. I've put them up partially to show that it's a little bit difficult to pull much sense out of the raw data. But what we did initially was plot on these polar plots the standard deviation of speed, the standard deviation of engine speed, and the peak frequency of engine speed to look at the potential effect of heading and also speed on those parameters. What's shown here is wave state 2, and we did similar data treatments for wave state 1 and wave state 3. Again, this is a similar presentation of data, but this time for course and steering results. And there is one thing I would like to point out on this. You'll notice standard deviation of course and the standard deviation of steering input in the bow, quarter, and waves. So there's sort of range of 0 to 90 degrees. We see much higher standard deviations of course and standard deviations of steering input than we saw in any other conditions. This might look like spurious data, but it was very apparent on board the boat that something different was happening in this specific condition. There was a very noticeable dynamic instability aboard the boat, and certainly we saw the same thing when we looked at the data. So I just want to highlight that, and we'll come back to that a little bit later. So in order to make a little bit more sense of the data, we decided to calculate the correlation coefficients between each pair of independent and dependent variables. And that actually allowed us to make a little bit more sense of what we were seeing. The 4 strongest correlations are shown on this slide. And the first one I'll highlight is a very strong correlation between speed and fuel consumption, which is potentially, not much of a interesting result since it's an expected result. The second set of strong correlation or relatively strong correlations we see are between significant wave height and the effort and success in maintaining speed. And the fourth one that's noteworthy is a correlation between wave steepness and the effort required to maintain course. So we're going to look at each of these in a little bit more detail, starting with fuel consumption. And the interesting thing with this is that I kind of hypothesized that we'd see significantly different fuel consumption rates in different wave states. But that wasn't the case. And fuel consumption rate is really only impacted by speed, with no real effect due to wave size or heading or any of the other things we tested. On the bottom left, you'll see a plot of fuel consumption versus vessel speed. It's a little bit hard to draw much of a conclusion from this data, but I will say that in some later work, we included not only the data from the star pattern tests, but also from the maneuvering and the endurance work we did. And when we put all that data together, which fills in the points in between the specific test speeds, you do see a very clearly the relationship between vessel fuel consumption and vessel speed squared in the non-planing, and then another curve in the planing region. In order to assess range, we decided to assume a 20% fuel reserve, and then calculated how far the vessel could go based on 80% of its fuel. We see a peak range occurring between 20 and 30 knots of boat speed for a maximum range of about 50 nautical miles. We trimmed all of the data out of this graph below 10 knots because any speeds slower than 10 knots really aren't reflective of the typical operational profile for this vessel. Their operational profile is essentially to get somewhere as quickly as they can, do some work, and come back as quickly as they can. Next, looking at the effort and success in maintaining speed, we saw a very strong correlation to significant wave height and a weak correlation to wave steepness. judging from what was observed aboard the boat, I expect this is due to the vessel's tendency to accelerate down and decelerate up the waves. And this was quite noticeable aboard the boat with some pretty significant longitudinal accelerations. It would be really nice to do some testing in additional wave states, but based on the 3 wave states we did, this is clearly what we saw. Like I said, it was obvious aboard the boat that something was a bit different and things were harder to maintain in the larger wave states. In the biggest wave, so in wave state 3, the operator was making very significant inputs to the throttle to minimize slamming and prevent kiting. Of course, slamming is when the boat comes down into the water and the hull slams into the water, and kiting is the opposite effect, where the boat has the potential to become airborne off the top of the wave. And kiting is a particularly dangerous condition because the boat can capsize if the wind catches underneath the hull of the boat. So to prevent this from happening, we noticed the operators making pretty significant throttle inputs, so a standard deviation up to about 3,000 RPM, with those adjustments being made every 2 to 8 seconds in wave state 3, depending on the heading. Like I said, we spent a fair bit of time talking to the operators and understanding their performance priorities, and they consistently rated the ability to quote unquote punch through waves as their top priority for engine performance. And it was clear that this is really because of the safety issues presented by kiting and slamming, they really needed to have that power available, so when they push the throttles forward, the boat does accelerate. And lastly, we'll look at the effort and success in maintaining course. Things were pretty consistent in terms of the ability to maintain course. Steering inputs were typically in the range of 2 to 4 degrees, being made every 4 to 8 seconds. Where we did see an increase was with increasing wave steepness, and the standard deviation of steering input went up to about 6 seconds in the most extreme cases. These seem like small numbers, but it's important to note that these, of course, are being measured at the angle between the engines and the transom. So the movements at the wheel that the operator is required to make are significantly larger. And for reference, 180 degrees at the wheel is approximately 5 degrees at the engine, which means that in the worst conditions, the operator is moving the steering wheel by an excess of 180 degrees every few seconds. I think it's a testament to the skill of the operators that they were very successful in maintaining course in all conditions. The standard deviation of course was pretty consistently around 10 degrees. We did see one exception, like we talked about earlier, at 38 knots in wave state 2 in the bow quartering waves. And it was noticeable aboard the boat and in the data. Now, we don't know why this happened, but just looking at planing hull theory, we could say it is potentially due to something, some combination or one of bow steering, chine riding, porpoising, engine trim, or the complex rib geometry. And I'd like to point to the complex rib geometry. It's not something I can confirm, but it seems that it could be due to the fact that the inflatable tube that surrounds the hull when the boat is planing is just a small distance above the waterline. So a small roll movement in the boat could foreseeably cause that inflatable ring to touch the water. And given the relatively large beam, we could expect that to induce a relatively large yaw moment and potentially cause some instability in yaw. And I'd love to be able to test that further at some point. So jumping to the sort of wrapping up phase of this, the first thing I will point out in the learning from this test is that our decision to use engine speed as a proxy for throttle input, while we were forced into it, it was not without its problems. I've shown again on the bottom left the time history of the steering input with the adjust, hold, adjust behavior. And we believe we see a similar thing in the throttle inputs. Well, you'll notice that the hold portions where we expect the operator is holding the throttle position constant has quite a bit of a variation. Given the fact that we're using engine speed, we cannot conclusively say whether or not that is a real user input. Our assumption that we've worked with is that variation in engine speed is due to something such as a variation of propeller loading rather than an actual human input. So we made that assumption in analyzing the data. But it would be much better if we're setting out to do this work specifically to measure throttle input directly. The second thing I'd like to point out, I think may be quite obvious, and that is that working in open high-speed boats presents very unique challenges, and we made our lives additionally difficult by testing in Newfoundland in late November and early December. So it was very cold, and indeed in the harbor in the morning. Sometimes we had to push our way out through some early season ice. What this meant was that we learned very quickly that a very detailed plan discussed with the crew before we left the dock was absolutely vital to making the day a profitable day out. We also learned, and luckily that we didn't have to learn this the hard way, that weatherproofing our expensive electronics was certainly a key challenge. That said, we didn't do such a good job of weatherproofing the people, and myself and some of the equipment I had on my person during the tests definitely felt a little bit the worst for wear after some of the days. One of the things that was a little bit alarming to me right at the beginning of the testing was that I've always been very happy knowing that the search and rescue boats are available. I'm a recreational sailor, and I have been pulled out of the water in the past as a teenager by one of these boats. They do provide a very flexible search and rescue asset. They're typically deployed in the busier areas around Newfoundland, more remote areas, and Newfoundland has a very large coastline that has a quite low user density. And a lot of areas are supplemented by larger Coast Guard vessels and aircraft, but they are specifically deployed in the higher density areas. They're fast, but their speed is very much impacted by wave conditions. And even the wave state 1, which I would consider to be pretty decent sailing weather, they cut the speed of the boat in half just due to the wave action. I would have loved to do some more work on the fundamental characteristics of the vessel. We didn't have the scope originally when we did the work to look at things like the natural roll response of the vessel. But a lot of the things that we can't really explain in the data, such as that dynamic instability at 38 knots in wave state 2, we might be able to explain if we've done a little bit more fundamental work to understand the reaction of the vessel. And the last sort of conclusion I'd like to pull out, I think this is the most useful thing that came out of this work for my purposes, is that we had, I believe, quite good success at adapting the automotive engineering field to the marine field, and using the assessments of driver performance that are used in the automotive engineering, I think gave some very interesting results. And I could see great potential for using this type of technique as a part of a vessel operator training or evaluation scheme, potentially even for assessing autopilot effectiveness. So before I stop talking, I would like to acknowledge a few people. One of our colleagues, Mr. Derek Butler, a technical officer at the National Research Council, he did all of the work to get this boat ready to test. He installed all of the instrumentation. He developed a relationship with the Coast Guard crew that got us up and running quite quickly. So his effort was very instrumental, pardon the pun, in getting the test program off the ground. We also owe a debt of gratitude in several ways to the search and rescue crew. As researchers, their professionalism and enthusiasm and willingness to work with us was absolutely crucial in this work. But also both myself and Trevor are recreational sailors in the area where these people provide coverage, and our lives are definitely much safer and lower stress knowing that we have such good individuals looking out for us.